Hey all AP1 kids, let's go through the 2018 AP exam I printed off for you, or actually I sent to you. We're going to go through the answers and figure out and make sure you understand what's going on. All right, here we go. The first question, we have a truck here. Look at that beautiful truck. And we're trying to figure out the forces acting on crate 2. Now crate 2 is being pulled to the right by the cable. So there's a cable force here. And there's also this force pulling it backward. Okay. There's friction as well, it says, because it's a rough road. And finally, block 3 is going to push block 2 to the right. So there are 3 arrows left and 1 arrow to the right. That's got to be C. Next up, we have this question. 2 blocks on a horizontal surface. This block's moving V0, and then they move off at V0 over 3. So the way I want you to think about this is the following. If these 2 blocks are equal, what speed would be going afterward? Yeah, V0 over 2. So this thing lost actually 2/3 of its velocity. So it's got to be lighter than the one it hit because it lost a lot more. Even my cat agrees. Come on, people. And that's why it's answer B. Then we have question number 3. Question number 3 involves this beautiful little graph of the velocity and time. And the first question says, what is the change object speed between 1 and 1.1? So from here to here, change in speed is just simply the idea of, change of velocity. So by looking at the numbers and centimeters per second from 1 to 1.1, that's got to be close to 5, actually probably less or so. But that's what it is. Next up, question number 4. The acceleration at 0.7 seconds. So right here, what's the acceleration? Well, acceleration is the slope of velocity. So we're going to find the slope of this line because it's change of velocity over time. So if we find the slope of that velocity, we end up with a number. But the question is asking, how do you actually find the slope? Well, you find the slope at the tangent line. And that's answer D. And number 5, frequency. Oh, geez. Oh, frequency is 1 over period. Period time takes go 1 full cycle. Looks like period's 0.6 seconds. So frequency is 1 over 0.6, which ends up being about 1.6. Cool. And let's keep moving on. Question number 6 and 7 we're not doing because they're wave things. So now we're on question number 8 down there. What we have is a block on a ramp. And the question asks, what is kinetic energy at the bottom of the ramp? Okay. Well, there's kinetic friction here, right? So we're going to say that the energy at the top equals the energy at the bottom plus the work due to friction. Because over here, it's got mgh. At the bottom, it's got that kinetic energy. And it lost some energy here. It lost work, which is force times distance. The force of friction is mu normal force. And the normal force you might remember is actually this term right here, which is mg cosine theta. And the distance it went down was L. So solving for K, it's mgh minus the work done. Force times distance. And that has to be answer C. Then we move on to question 9. Another graph. Imagine our surprise. Here's a graph of force and time. Force and time screams impulse. In this question, which is the following change in momentum? Hey, change in momentum is impulse. Impulse is force times time. Force and time means area, right? Tell them that. Come on. Now she won't talk anymore. That's sad. So we're going to find the force and time between 0 and 4. Okay, this looks like a triangle and a square. So if you find the total areas, add them up, you get around 30. Number 10 is electricity, which we're not going to do. Number 11 is kind of gravity, which I don't think we're supposed to do, but just in case you forgot, they're going to have the greatest speed when these things are closest together, and that's at 0.4. Now, to question 12. Here we have a ramp ball goes down and then flies in the air. This looks like penny lab section and like kinetic energy stuff. This is the cylinder though. Cylinders, might remember, have that rotational kinetic energy. As the cylinder rolls down the ramp, how does the potential energy of the cylinder Earth and the kinetic energy change? Well, potential energy of the cylinder goes down because of the fact that it's getting a little closer to Earth, and the kinetic energy goes up. That has to be answer C. But once it's in the air, how does the rotational linear compare? Well, it's in the air. Is there a force causing it to twist more? And the answer is no. So the kinetic energy rotational stays the same because of the fact that there's not a force causing, there's not a torque causing it to rotate more. But it is going to gain kinetic energy regularly because potential is going down because gravity is working on it. So kinetic energy translational, aka linear, must go up. Same rotational, increased kinetic energy. That has to be answer C. And then finally, a sphere with the same mass and radius, but a smaller inertia. Ooh. Okay, so that means that I goes down. How does the sphere and cylinder energies compare at the bottom? Well, the total amount of energy has to stay the same. So it has to be D. The total amount of kinetic energy is the same. Now, the share that's kinetic and rotational will be very different. You can probably understand that the sphere has less rotational kinetic energy and has more translational kinetic energy, but overall the kinetic energy is the same. It had the same change of potential. That's why they have the same energies, just different amounts of each form. But they had to be the total. 15 is easy, but we don't have to do it because of the fact that AP and coronavirus. So let's go to 16. Hey, loop-de-loop, this looks familiar. Small block slides down without friction, and it remains firmly in contact here. So it has more than enough speed. So if you think about it, that means that there have to be two forces down. There has to be the normal force and mg. You might remember, when it just barely makes a loop, the normal force goes away, and it's just mg. So the acceleration here must be larger than gravity because there's more than just mg there. And it is. There's more of an inward force than gravity because as you go faster than that minimum speed, you get more and more centripetal acceleration. Question 17. A pendulum bob is raised to 1 meter. The bob then goes to be 0.8 meters. What's the speed? Well, this looks like straight up energy. The potential energy at 1 equals potential of 0.8 and the kinetic energy. So mass is 0.5, so I'm going to do mgh equals mgh plus 1/2 mv squared. Here it's all potential, here it's some potential, some kinetic, solving for velocity, and you end up with around 2. Life is good. Hey, not too bad so far. Then we get to these weird RAM things. This is question 18. We have a block released from rest. Then you repeat it, but this time you give it a shove. What's mechanical energy compared before? Well, mechanical is potential plus kinetic. As you can probably imagine, in the first case, when it starts with no shove, it has the same potential. When you give it a shove, it now has more kinetic, when it has more mechanical. So when it reaches the bottom, it's got to have more energy than before because of that fact. Again, in summary, when you don't give it a shove, it just has potential to start off with. When you give it a shove, it's potential and kinetic, and the total amount stays the same. Next up, an apple. Physicists love apple questions because of the whole Newton thing. Don't tell me why. In question 19, an apple is least from less 500 meters above the ground. So 500 meters, we have an apple. I'm not using red for my apple, sue me. And due to combined resistance and gravity, it has a speed of 40. But it shouldn't, because we're figuring out what percentage of energy is lost. Okay, so what we're going to do is we're going to say it started with potential energy of mgh. That's h, g, m. So I have 5,000 m. And it ends with just kinetic energy, which is 1/2 mv squared, which ends up with 4,200 m. So obviously some energy is lost. We're trying to find the energy that is dissipated. Yeah. Okay. Wait, no, hold on. This is sorry, I did this wrong. This is 800. I'm about to say. So we lost 4,200. That's the energy we lost. And the total amount of energy we have is 5,000. That percentage is 84. You do that correct. I'm so sorry. This is 800 that you end up with. So you lost 4,200. Now, question 20. Which I remember doing a lab, actually online simulation with me to help understand it. Question 21 referred to the following situations. We have a shot up at 45 degrees, shot down at 45 degrees, shot to the side at 0. These are all the same velocity. Which of them relates to the vertical component right before it hits the ground? Okay. Excuse me. Here's how I need you to think about this. The vertical component. This starts with a vertical of 0. It starts off with some number. It starts off with the same number. Just one's positive, one's negative. Doesn't matter. When this hits, it's going to gain some velocity from that. So it goes from v0 to some number. This is going to gain the same amount, but you're adding on to a larger number to begin with. So this will hit with a larger velocity than this. This will hit with equal velocity because eventually it comes back to the same point with the same speed as that. So 1 and 2 are going to have the same speed, but more than 3. Again, because they're going to gain the same velocity change from this height, but the final speed is what you get compared to the beginning. If y'all gain 10 from this, this will end up with 10 overall. This will end up with 10 plus that number. This will end up with 10 plus that number. And that's why these two hit with more speed. Now for question 21. Rock 1 reaches a maximum height h max after being launched. It's asking, hey, what is the work done on the entire time? Well, first thing you should know, work is a force times distance. And hey, gravity acts this way. And what total distance did it go this way? 0. Oh yeah, so the work done is 0. AKA, did it change speed from here to here? No, these 2 points should have the same speed, which means there's no change in kinetic energy overall, which means there's no work done. And then we have a marshmallow gun, one of my faves. Our marshmallow gun, 2.5 grams. Better convert this to kilograms. Heck yeah. So the mass is 0.0025 kilograms because you divide by 1,000. I have a 40 centimeter pipe. So the length of the pipe is 0.4 meters. Again, you don't want to do that. And it's asking, what is the speed if you have the net force is 0.7? So the first thing you do is you're going to say net force equals ma. You're going to solve for the acceleration, which you get around 280. Then, because it's a constant acceleration, we're going to use kinematics, quarter 1. We're going to say the final velocity squared is the initial velocity squared plus 2ad on your formula sheets. The final velocity is what we're trying to find. The initial velocity is 0. 280 times 0.4. Solve that and you get 15, which is what C is. 23. Hey, we have meter stick being held up, and then as the meter stick falls, what's the center of mass going to do? Well, even though this is going to kind of swing down, the center of mass is right here. It's the only force being felt is gravity, just straight down. So the center of mass is not going to change. Since the force is at the center of mass is going to move straight down. And there we are. 24, 25, 26 we don't do because those are waves and electricity stuff, even though they're not too bad. And then we get to our torque stuff, 27. So here we have multiple forces on it. It's asking which one creates the largest change in angular momentum. Well, you know that torque times time is the change in angular momentum, kind of like a force in time is the change in regular momentum. So basically, which one of these is the largest torque? Torque is F times R perpendicular. I call it distance 1, 2, 3, 4. You can do that. Like for example, here, if you call this 4, you get 160. Here you get 180. 60, 150. Obviously, this is the largest one. It'll cause the biggest change, and that's the 60 newtons force, which is C. Same thing here. We have a disk with a radius and a force. This is going to make a torque, of course. And it's asking, hey guys, what is the angular speed going to be after 1 second? So we have 1 second of time, radius of 0.5, force is 2. We can get the torque then to be 1 newton. And torque equals I alpha. So in order to figure out the speed, we need to know I. That's not here. Because I know alpha is a change in velocity over time, but I need to know this. Since I don't have it, can't do it. 29, more rotation. We have a rod with a pivot point here, and 3 equal forces are shown. What's this thing going to do? Well, originally, apparently, it's spinning counterclockwise, so that's that way. As you can probably imagine, this will be the biggest torque, so it's going to go that way. So these two are opposing. So the angular speed is going to decrease at first, and then it'll eventually rotate the other way. So right after this time, it's still going to go counterclockwise, but it's going to be slowing down. Eventually, it's going to stop and go the other way. The time it takes, we don't know because we have to know what the actual numbers are. In question 30, 2 systems are in oscillation, a pendulum and a block on a spring. By the way, I hate this question. I'll find out why in a second. The block spring system takes twice as much time. Well, period of this is 2 pi squared L over G. The period of this is 2 pi squared M over K. And this one takes twice the time. Which of the two can you make to make them have the same time? Well, you can make this one go up or this one go down. To make this one go down, you want the mass to go down or the K value to go up. To get this thing to go higher, you want L to increase or you want gravity to increase. Increase the mass of the pendulum, that is nothing. Increase the angle, that is nothing. Decrease the mass of both the block and the pendulum. Ugh! Technically, doing this doesn't change a damn thing, which is why. But yeah, okay. Yeah, that's it. 31, 32 refer to the stuff we're doing a sound, which we won't do, which is sad. And then we have 33, whoop-de-dee. A ball at an angle. Boom. Projected into the air. There's air resistance, though. Ooh. So air resistance is going to be affecting the opposite way it's moving. So at time t, it's moving up to the right of 45. So at this point, there's going to be gravity down, and there's air resistance this way. Combine the two, you end up with the acceleration that way, which has to be bigger than gravity. Because there are 2 forces working against it. This is just this is just G, and this is bigger. This is also pretty big, so if you combine them both, you have to get bigger than gravity. So the only option for that has to be B. Oh, I threw this away temporarily. I'm so sorry, because I have to do 34 and 35. All right, center mass stuff. We have 2 figure skaters moving together, then they separate. Which point is going to be for skater 2 if skater 2 is twice as light? How much you think about this? At 2 seconds, the system moved that much. 1, 2, 3, 4. The system doesn't change if you separate. So at this point, 1, 2, 3, 4, here's where the system would be after 4 seconds. But the heavy person moved 2 blocks that way. So the lighter person better move, 1, 2, 3, 4. It should be an A here, sorry. There we go. That's 2 blocks. So the lighter person must move twice as far, 4 blocks, this way, which is D. Again, the way I think about it, the system doesn't change. But if the heavier person ends up here, the lighter person has to end up here to cancel it out. And then for 35, charged sphere, can't do it. Poop. 36, the last of our single answer multiple choices. Here we have two impulses. I'm sorry, we have two works, because work is force times distance. Force and distance, force and distance. Compare the work sum then. Okay, if it's multiplication, it's area. So it's basically asking, how do the areas of these two compare? Well, you can see that work 2 is much bigger because of the fact that it's curved. Now look at their explanations. Their explanation is C. They're saying that the average force is less, which is kind of true. But I would say because the areas are different. And this bottom statement does not back that up whatsoever. Midpoints don't matter. It's about the average force over the average distance. And then we end up with the 2 correct answer sections. Here we have a water skier moving to the right with acceleration A. So we have a force of the rope, which is Ft, what they call it, or just T. There is drag force. And there's also a vertical lift. And they're saying that the person is accelerating this way. This is straight up old school forces. So we're going to say net force are these two subtracted, with this as MA. And these two are equal. So instead of writing MA, I'm going to put 0. So I need to figure out which one of these are true. Well, obviously this is A. And this is C. And those are my 2 answers for it. In question 32, we have acceleration versus time. Okay. Small dip, big dip. So in 132, we have 2 cars. The accelerations, which of the following states and dates are correct? Okay. Acceleration 0, 0. I want to find velocity. No, I want to find the maximum peak at 10.05 seconds. No, that's not true at all for part A. They don't reach maximum speed. Remember, this is the entire time they're accelerating. So that means they reach their highest speed at the end point, because the entire time their acceleration. The acceleration is changing. Oh my god, my cat's running around like a maniac, because even she's running with acceleration. So the area of this is the velocity, which you calculate, might remember, is called the integral. So this is the integral the entire time. It's not the max speed. B, the cars experience approximately the same impulse. Yeah. Force times time. Force time graphs, the area is the impulse. And from this, it looks like they have the same area. So that means they have the same impulse. Car B experiences a non-zero force for a longer distance than A. Car B experiences non-zero force. No, it's less time. Boo. It's got to be D. Change of momentum, car B occurs over a shorter period of time. Yeah, B takes less time than A. 133. The graph shows a truck is moving along a straight level road. How do you determine D? Okay, I have velocity and time. So let's go through them. A, multiply the average speed of 18. So look at the middle. By the 10-second travel time. Yeah, that works. Because you might remember, we did that before when we did like the, if something goes from like a speed of from 10 to 20 in 1 second, we say the average is 15. And for 1 second, that'd be 15 meters. So yeah, look at the average point, as long as it's not changing. Multiply half initial speed by 30 by the 10. No, that's not good. You don't want to do initial because it's changing. Look at the slope of the line. Oh, the slope of the line gives you acceleration. And distance is, nope, that's not true because you need initial velocity t. So no, that would tell you how much it changed by, but it wouldn't tell you how fast it's going. And even then, yeah, no. You need to add initial velocity t term. Finally, calculate the area beneath the line on the graph. Yep, that works as well. So it's B and C. And then 134, which I kind of let you do, but like I don't know if it's really under the gravity stuff or not, because it might be under forces. So I just did it anyway, because even though you might not have to. Gravity on Mars is less. So, which is following is true. The vehicle weight was constant until it reached the surface of Mars. No, that's not true. It changed, because gravity gets weaker as you get further away. The weight increased while ascending. Yeah, as you get closer to the planet, you get more force. The weight always equals blah, blah, blah. Nope, that's not true. The normal force is 0 unless you actually hit it. The vehicle weighed less on the surface of Mars than Earth. Yeah, Earth has a value of 10, so of course it has to weigh more on Earth rather than Mars. Nice job, guys. Take a nice little break, pause this video, get ready for the FRQs that you should have done. And you're back. Okay, here we go. Here's the first question. We have this really weird spinning ball. 2 balls, I'm sorry, on a thing. So the first question it says is, draw the horizontal and vertical components of the center. The center doesn't care about the spinning. So if something's in the air, we know for sure. The x velocity is constant. The y velocity is thrown upwards. It goes from positive to negative, with the slope is negative 10. The slope here is 0. Because ax is 0, ay is negative 10. And then there's more. Now it says, okay, please figure out and draw the forces on this ball. Well, there's a tension force because this one's pulling on it, and there's also gravity. The only 2 forces there. You're not going to draw torques or stuff like that because those aren't actual forces. And then draw for the whole toy. Well, the whole toy, its center of mass is just one force, mg. And finally, for triple I, it says, when the toy is released, it was moving along initially to 15 meters, blah, blah, blah. It was at 15 at 60. Calculate the speed at the center of the string or the system at the top of its trajectory. Hey guys, what's the y velocity at the top? 0. What's the x velocity? The same as in the beginning. Let's do 15 cosine 60, and you get 7.5 meters per second, because the x velocity doesn't change. Only the y velocity changes because gravity in the x is 0. And then the famous make a lab question. These are always true. A heavy lab hits a lighter cart. Okay. They hit, but there's some energy lost. And the kid says, hey, I think you lose more energy if you start off and hit at a faster speed. They said that K loss over K initial is a percentage. So first thing I want to ask you is, do this why the hypothesis is correct. I said at a faster velocity, the impact has more, let's say, compression, or it has more moving internal mass. All this stuff takes energy from the system. And that's why the faster you go, the more impact it's going to have, the more it's going to move the molecules inside the cart. B, design an experiment. Okay. You probably should understand, if you want to figure out the change in kinetic energies, you need to figure out the velocity initially of the cart, the mass of the carts, the velocity of the carts after. V0, M1, M2, V1, V2. Equipment. Motion detectors and scales. So what am I going to do? I'm going to get the M's first. Then I'm going to measure the velocities of all 3 things, before and after, in the experiment. But then the really important thing, the one they really care about, you're going to do multiple trials of each instance, and then you're going to vary the initial velocities multiple times. So for example, you might run it at 1 meter per second, do it 3 times, take the averages. Then you can run it at 2 meters per second, do it 3 times, 3 meters per second, so forth, so forth. They want you to run multiple trials of each time you do it. And then you do calculations. C, the calculations determine how you can actually get values. So what I said is, okay, I'm going to do 1/2. This is the initial kinetic energy. And I'm going to do So I'm going to do those 2 things multiple times. And then what I'm going to do is I'm going to do K lost is KEI minus KEF. I'm going to look at that fraction that student did, K lost over KEI. And I'm going to make a table. And I'm going to see how the numbers, I'm going to see if there's a trend there. For example, as the numbers go up at what speed I had, this percentage or fraction should go up as well. If I see this trend of it going up, I know that more velocity equals a bigger loss. If they're all the same number, that means there's not a value. And finally, letter D, which is actually kind of difficult. It says, consider a different scenario when the cards sit together. Determine the expression for the fraction. Okay. If they sit together, it's momentum. The initial momentum of the first card becomes, and they sit together, something for VF. So this right here is how much it changed by, the final velocity. So if you think about it, this is kind of the relationship here. So if your initial velocity, let's say, was, 2, this would bring it down to what your final velocity is. So what I thought about it is if the final velocity is 2/3 of V naught, then this will be 3/2 because it's like on the other side of the fraction. So if I want to find what fraction energy is lost, it's just the opposite of this. This is the fraction of energy it's lost because the final velocity times that is kind of the relationship based on it. Weird, kind of not intuitive, but that's kind of what letter D would be. If you actually want to go through and try to put this in, you get this exact result the same way. If you want to put this into kinetic energies and try to solve for it, but it's a lot of work. You don't have that much time on it. You probably have to give it a quick shot like that. Now, what's weird on this for a little quick is that questions 3 and 4 are ones you should not do because of it. I don't know how the AP is going to do it. But this wave question, which we wouldn't know how to do very easily, no longer happening. The electricity equation, which is even better and easier, unfortunately, you're not going to do. So it comes down to this final question 4, where we have a block going up the ramp and down the ramp, an example we literally did in class. So going up the ramp, if you draw the forces, gravity, normal force, friction going this way. Going down the ramp, still gravity, still normal force, but now friction is going the opposite way. The block takes some time to go up the ramp. How does going up and going down compare? Here's what I want you thinking. As it's going up the ramp, gravity and friction are both working the same way, meaning that the acceleration is huge, and it's really going to slow down quick. Because gravity and friction are working with each other. But here, gravity and friction are working against each other, so it's a tiny acceleration, which means it's a very low acceleration. It'll take a lot longer. It'll go up, quickly stop, and take this more time to go down the same distance. So the time going down is bigger than the time going up. And again, I said, because going up, mg sine theta and friction are together, creating a huge acceleration, which means you have a quick time. Going down, it's mg sine theta minus friction, which is a tiny acceleration, which means you have a long time. Guys, that was AP1 on an exam. We're going to have some more stuff coming soon. Thank you for your time.